saturated solution of manganese hydroxide at 25 degrees Celsius, the concentration of manganese 2 plus ions is 1 times 10 to the negative fifth moles per cubic decimeter. The solubility product of magnesium hydroxide at 25 degrees Celsius is 1 times 10 to the negative 10th, and the Kb value of ammonium hydroxide at 25 degrees Celsius is 1.6 times 10 to the negative 5th. Question number 1. Calculate the solubility product of manganese hydroxide at 25 degrees Celsius. Concentration of manganese 2 plus ions in the saturated manganese hydroxide solution is 1 times 10 to the negative fifth. We have to calculate the solubility product or Ksp of this manganese hydroxide solution. In saturated solutions, usually the solid manganese hydroxide is in equilibrium with the aqueous manganese 2 plus cations and the aqueous hydroxide ions. Solubility of manganese 2 plus ions is given 1 times 10 to the negative fifth. Then solubility of hydroxide ions, you can see the coefficient 2 is there. Therefore, it's twice than that of Mn2 plus ion. So, we can write 2 times 10 to the negative fifth moles per cubic decimeter. Ksp equals manganese 2 plus concentration times hydroxide ion concentration to the power 2. Substitute values. Manganese 2 plus concentration 1 times 10 to the negative fifth moles per cubic decimeter times hydroxide concentration 2 times 10 to the negative fifth moles per cubic decimeter power 2. 1 times 10 to the negative fifth, then 4 times 10 to the negative 10th. Therefore, Ksp of manganese hydroxide at 25 degrees Celsius is 4 times 10 to the negative 15th mol third dm negative 9th. Question number 2. Calculate the concentration of hydroxide ions in a 0.01 moles per cubic decimeter ammonium hydroxide solution at 25 degrees Celsius. Ammonium hydroxide is a weak base. The concentration of the given ammonium hydroxide solution is 0.01 moles per cubic decimeter, and the base dissociation constant or this dissociation constant of ammonium hydroxide is also given in the question, and we need to calculate the OH minus or the hydroxide ion concentration of this weak basic solution. This weak base ammonium hydroxide undergoes partial dissociation and produces ammonium ions and OH minus ions in aqueous solution. Initial concentration of ammonium hydroxide is 0.01 moles per cubic decimeter. If the dissociated amount from this weak base is X, we can write the change as minus X, and the produced concentration of ammonium ions as well as OH minus ions are also X because the stoichiometry is 1:1. At equilibrium, the remaining concentration of ammonium hydroxide is 0.01 minus X, and the ammonium concentration as well as OH minus concentration at equilibrium is X moles per cubic decimeter. Since ammonium hydroxide is a weak base, or we can see the Kb value is really less, this dissociation X is negligible. We can write 0.01 is very much greater than x. Therefore, 0.01 minus x we can assume as 0.01 moles per cubic decimeter. Next, we can see the concentration of ammonium ions as well as concentration of OH minus ions produced from ammonium hydroxide is X. That means ammonium hydroxide concentration is equals to the OH minus concentration at equilibrium. Write the Kb expression for the ammonium hydroxide. Kb equals ammonium ion concentration times OH minus ion concentration divided by the concentration of ammonium hydroxide. We found that ammonium ion concentration and OH minus ion concentration at equilibrium is the same. Therefore, we can write OH minus ion concentration equals square root of Kb times ammonium hydroxide concentration. Substitute values for this equation. Kb equals 1.6 times 10 to the negative fifth moles per cubic decimeter. Concentration of ammonium hydroxide 0.01 moles per cubic decimeter. Square root of 16 times 10 to the negative 8th. 4 times 10 to the negative 4th moles per cubic decimeter. Therefore, concentration of hydroxide ions in the 0.01 moles per cubic decimeter ammonium hydroxide solution is 4 times 10 to the negative 4th moles per cubic decimeter. Question number 3. Determine the concentration of ammonium hydroxide necessary to start precipitation of manganese hydroxide from a 0.001 moles per cubic decimeter solution of manganese sulfate. Here we have 0.001 or we can write 1 times 10 to the power negative 3 moles per cubic decimeter manganese sulfate solution. Manganese sulfate is a strong electrolyte. It dissociates completely and it gives manganese 2 plus ions and sulfate ions into this solution. When ammonium hydroxide is added, it partially dissociates and it gives ammonium ions and OH minus ions to the solution. Manganese 2 plus ions comes to the solution by the direct dissociation of manganese sulfate and OH minus ions comes to the solution by the partial dissociation of this weak base ammonium hydroxide. When this ionic product is the product of manganese 2 plus concentration and OH minus ion concentration, when this ionic product is greater than Ksp, we can see the precipitate of manganese hydroxide in this beaker. The question asks the concentration of ammonium hydroxide necessary to start precipitation. This is the beginning of this precipitation process. Here we have to consider the saturated solution without precipitation. At this point, Ksp equals ionic product. Now we will substitute values for this equation. Ksp of manganese hydroxide we have calculated during the question number 1. Then concentration of manganese 2 plus. We know the concentration of manganese sulfate. Therefore, manganese 2 plus concentration is the same. Therefore, we can calculate the minimum concentration of OH minus ions to start this precipitation. Ksp 4 times 10 to the negative 15th mole third dm negative 9th Manganese concentration is 1 times 10 to the negative third moles per cubic decimeter times OH minus concentration to the power 2. OH minus concentration is the square root of 4 times 10 to the negative 12th. The answer is 2 times 10 to the negative 6th moles per cubic decimeter. This is the hydroxide ion concentration necessary to start precipitation of manganese hydroxide. Ammonium hydroxide is a weak base. Therefore, concentration of ammonium hydroxide is different than the concentration of OH minus ions at equilibrium. This is the concentration of hydroxide ions required to start the precipitation of manganese hydroxide. But the question asks the required concentration of ammonium hydroxide to start precipitation of manganese hydroxide. We assume the concentration of ammonium hydroxide is C moles per cubic decimeter. Then the dissociation, this is minus x, plus x and plus x. So at equilibrium, C minus x, x and x. So we have found this value of x. So that is 2 times 10 to the negative 6 moles per cubic decimeter. This dissociation X is very much less than the concentration of C. So we can assume concentration of ammonium hydroxide at equilibrium as C. We need to calculate this concentration of ammonium hydroxide using the concentration of OH minus ions. For that, we can use the Kb expression of ammonium hydroxide. Kb equals ammonium ion concentration times OH minus ion concentration divided by ammonium hydroxide concentration. During question number 2, we proved that hydroxide ion concentration and ammonium ion concentration are the same. Therefore, we can write OH minus ion concentration to the power 2 divided by ammonium hydroxide concentration. Ammonium hydroxide concentration is OH minus ion concentration to the power 2 divided by Kb. Substitute values for this equation. Hydroxide ion concentration required to precipitate manganese hydroxide is 2 times 10 to the negative 6th moles per cubic decimeter to the power 2 divided by Kb ammonia is 1.6 times 10 to the negative 5th moles per cubic decimeter. 4 times 10 to the negative 12th divided by 16 times 10 to the negative 6th. 2.5 times 10 to the negative 7th moles per cubic decimeter. Therefore, the concentration of ammonium hydroxide required to start precipitation of manganese hydroxide is 2.5 times 10 to the negative 7th moles per cubic decimeter. This is the answer for the question number 3. Question number 4. If 5.35 grams of ammonium chloride is dissolved in 1 cubic decimeter of 1 moles per cubic decimeter ammonium hydroxide solution, calculate the concentration of hydroxide ions in the solution. 1 mole of ammonium hydroxide is present in 1 cubic decimeter solution. Therefore, concentration of ammonium hydroxide in the solution is 1 moles per cubic decimeter. First, I will discuss the theory behind this question. Ammonium hydroxide is a weak base. Therefore, it dissociates partially in this aqueous solution to produce ammonium ions and OH minus ions. When this solid ammonium chloride is added, it completely dissociates into ions because it's a strong electrolyte. Therefore, ammonium chloride gives ammonium ions and Cl minus ions into the solution. Because of this excess ammonium ions comes to the solution with ammonium chloride, concentration of ammonium ions increases in this solution. Therefore, according to the Le Chatelier principle, this dissociation goes on reverse direction. That means it produces less OH minus concentration than in a pure solution of ammonium hydroxide. So this is a common ion effect. Always in the presence of common ion, these weak bases gives less OH minus concentration than in pure aqueous solutions. To continue the question, we need the concentration of the added ammonium chloride. First, we will calculate the number of moles of ammonium chloride added into the solution. Number of moles equals mass divided by the molecular mass. Mass of added ammonium chloride is 5.35 grams divided by the molecular mass 53.5 grams per mole, 0.1 moles. Therefore, concentration of ammonium chloride is 0.1 moles per cubic decimeter. The volume of this solution is 1 cubic decimeter. Therefore, number of moles is the same as concentration. Now we will write down these dissociation equations. When solid ammonium chloride dissolves, it completely dissociates into its aqueous ions and it produces aqueous ammonium ions and Cl minus ions. Ammonium hydroxide is a weak base and it partially dissociates in aqueous medium to produce ammonium ions and OH minus ions. The concentration of ammonium chloride is 0.1 moles per cubic decimeter. Therefore, concentration of ammonium ions as well as chloride ions produced from ammonium chloride has the same concentration. Initial concentration of ammonium hydroxide is 1 moles per cubic decimeter. If the dissociation of ammonium hydroxide is X, the produced concentration of ammonium ions as well as OH minus ions also X moles per cubic decimeter. Therefore, at equilibrium, the concentration of ammonium hydroxide is 1 minus X ammonium as well as OH minus ion concentration is X moles per cubic decimeter. 1 is very much greater than X. Therefore, 1 minus X is almost same as. Next, we will write the Kb expression. Kb equals ammonium ion concentration times OH minus ion concentration divided by ammonium hydroxide concentration. In this example, ammonium ion concentration and OH minus ion concentrations are not the same as previous questions. The reason is more ammonium ions comes to this aqueous solution from the dissociation of this strong electrolyte ammonium chloride. Total ammonium ion concentration is the sum of the concentration of ammonium ions from ammonium chloride and the concentration of ammonium ions from ammonium hydroxide. concentration of ammonium ions comes from the dissociation of ammonium chloride is 0.1 moles per cubic decimeter. Then concentration of ammonium ions comes from the dissociation of this weak base. Ammonium hydroxide is X moles per cubic decimeter. But X is very much less than 0.1. Therefore, concentration of ammonium ions in the beaker is 0.1 moles per cubic decimeter. Before substituting values, we can rearrange this equation. OH minus ion concentration equals divide by ammonium ion concentration. Now, substitute values for this equation. Kb equals 1.6 times 10 to the negative fifth moles per cubic decimeter. Concentration of ammonium hydroxide 1 moles per cubic decimeter divided by concentration of ammonium ions. We have calculated concentration of ammonium ions is the same as the concentration of ammonium chloride. Because in the presence of this common ion, dissociation of the weak base is very much less than that when compared to the dissociation of this weak base in the pure aqueous solution. Therefore, concentration of ammonium ions in the solution is 0.1 moles per cubic decimeter. 1.6 times 10 to the negative fourth moles per cubic decimeter. Therefore, concentration of OH minus ions in this solution is 1.6 times 10 to the negative fourth moles per cubic decimeter. This is the answer for the question number 4. Question number 5. Calculate the number of moles of solid ammonium chloride required to prevent the precipitation of magnesium hydroxide in a solution to be made by mixing 0.5 cubic decimeters of 0.02 moles per cubic decimeter solution of magnesium nitrate and 0.5 cubic decimeters of 0.2 moles per cubic decimeter solution of ammonium hydroxide. First, I will explain the theory behind this question. Aqueous magnesium nitrate contains magnesium 2 plus ions and nitrate ions. Because magnesium nitrate is a strong electrolyte, so it completely dissociates into ions. Ammonium hydroxide is a weak base, therefore it partially dissociates and produces some amount of ammonium ions and OH minus ions. The concentration of these two solutions are given. Magnesium nitrate is 0.02 moles per cubic decimeter. Ammonium hydroxide solution it is 0.2 moles per cubic decimeter. Both volumes are 0.5 cubic decimeters. When these two solutions are mixed together, a dilution takes place. Therefore, these two concentrations will be decreased in this final solution. Therefore, the first thing you have to do is write the concentration of these diluted solutions, because we need the concentration of these diluted solutions to proceed with the calculation. When these two solutions are mixed together, volume doubled. Therefore, these two concentrations becomes half in this mixture. We can write magnesium nitrate concentration 0.01 moles per cubic decimeter. Then ammonium hydroxide concentration 0.10 moles per cubic decimeter. All students, you can calculate this using the dilution equation. C1V1 equals C2V2. What you need to calculate is the C2 or the final concentration. We know the initial concentration, then initial volume as well as final volume. Now we will move to the reaction mixture. Magnesium 2 plus ions and nitrate ions were present, which was coming from magnesium nitrate. Then this ammonium hydroxide, it undergoes partial dissociation. So ammonium ions and OH minus ions also present in the mixture. When magnesium ions present with OH minus ions, there is a possibility of forming the magnesium hydroxide precipitate. When ammonium chloride is added to the solution, it gives ammonium ions and Cl minus ions. Now we have to consider the common ion effect. When the ammonium ion concentration increases, this dissociation reaction goes on the reverse direction. Therefore, it produces less concentration of OH minus ions. Again, moving back to the question, what we need to calculate is number of moles of solid ammonium chloride required to prevent the precipitation of magnesium hydroxide in this mixture. When the ionic product, that is a product of concentration of magnesium 2 plus and OH minus ions, when this ionic product is greater than Ksp of magnesium hydroxide, we can see the precipitate of magnesium hydroxide. Then, when solid ammonium chloride is added, ammonium ion concentration increases. Therefore, according to Le-Chatelier principle, this dissociation goes on the reverse direction. It gives less OH minus concentration. With increasing concentration of added ammonium chloride, OH minus ion concentration decreases. Therefore, ionic product decreases with the addition of ammonium chloride. If the ionic product is less than Ksp, a precipitate will not form. For this question, we have to consider a saturated solution of magnesium hydroxide. In that case, Ksp equals ionic product. Now we will move to the calculation. This is the equilibrium between solid magnesium hydroxide and the respective ions. The concentration of magnesium 2 plus in this solution is 1 times 10 to the power minus 2 moles per cubic decimeter. Ksp value of magnesium hydroxide is given in the question. Now we know the concentration of magnesium 2 plus ions in the solution, but we don't know the concentration of OH minus ions because concentration of ammonium hydroxide is not the same as concentration of OH minus ions given by this ammonium hydroxide solution. Therefore, using the Ksp expression, we need to calculate the concentration of OH minus ions in this solution. Ksp equals magnesium 2 plus ion concentration times OH minus ion concentration power 2. OH minus ion concentration equals square root of Ksp divided by the magnesium 2 plus ion concentration. Now substitute values for this equation. 1 times 10 to the negative 10th mol power 3 dm negative 9. 1 times 10 to the negative second moles per cubic decimeter. The answer is 1 times 10 to the negative 4 moles per cubic decimeter. Therefore, OH minus ion concentration in the mixture is 1 times 10 to the negative 4 moles per cubic decimeter. Ammonium chloride completely dissociate and produce ammonium ions and chloride ions. The weak base ammonium hydroxide, it undergoes partial dissociation. Initial concentration of ammonium hydroxide is 0.1 moles per cubic decimeter. And the OH minus ion concentration at the end we have calculated as 1 times 10 to the negative 4 moles per cubic decimeter. Therefore, the produced amount of ammonium ions also 1 times 10 to the negative 4 moles per cubic decimeter. Then at equilibrium, the concentration of ammonium hydroxide ions is 0.1 minus 1 times 10 to the negative 4 moles per cubic decimeter. This dissociation is very much less than the initial concentration. Therefore, 0.1 minus 1 times 10 to the negative 4 is equals to 0.1 moles per cubic decimeter. We assume the initial concentration of ammonium chloride is Y moles per cubic decimeter. Then the ammonium ion concentration and the chloride ion concentration is also Y moles per cubic decimeter. Therefore, total ammonium ion concentration is Y plus 1 times 10 to the negative 4. Y is very much greater than 1 into 10 to the power negative 4. Therefore, we can write the ammonium ion concentration equals to Y moles per cubic decimeter. What we have to do is to calculate the mass of required solid ammonium chloride. Before calculating the number of moles, we have to calculate the concentration of the required ammonium chloride, which is Y. This Y can be calculated using the Kb expression. We know the concentration of ammonium ions, concentration of OH minus ions, and the concentration of ammonium hydroxide. Therefore, Y can be calculated using this expression. This is the Kb expression. Ammonium ion concentration equals Kb times ammonium hydroxide concentration divided by OH minus concentration. Substitute values. Kb equals 1.6 times 10 to the negative 5th moles per cubic decimeter times ammonium hydroxide concentration 0.1 moles per cubic decimeter. OH minus ion concentration is 1 times 10 to the negative 4th moles per cubic decimeter. Ammonium ion concentration is 1.6 times 10 to the negative 2 moles per cubic decimeter. The total volume of the mixture is 1 cubic decimeter. Concentration of ammonium chloride is also the same. 1.6 times 10 to the negative second moles per cubic decimeter. The volume of the mixture is 1 cubic decimeter. That means number of moles of ammonium chloride in the solution is 1.6 times 10 to the negative 2. We can calculate the mass. Mass of ammonium chloride is number of moles times molecular mass. Number of moles 1.6 times 10 to the negative second moles multiplied by the molecular mass of ammonium chloride, 53.5 grams per mole. Therefore, the required mass of ammonium chloride is 0.856 grams. This is the answer for the question number 5. Question number 6. Explain the use of ammonium chloride in group analysis. Now we will move to the cation analysis, group 3. The reagents of group 3 in cation analysis are ammonium chloride and ammonium hydroxide. In the presence of these two reagents, Fe3 plus ions, chromium 3 plus ions and aluminium 3 plus ions give the respective hydroxide precipitates. Now we will discuss the theory behind this precipitation. Ammonium chloride completely dissociate into ions and produce ammonium ions and chloride ions. Ammonium hydroxide partially dissociate and produce ammonium ions and hydroxide ions. Because of these ammonium ions produced by ammonium chloride, ammonium ion concentration increases. Because of this high ammonium ion concentration, according to the Le Chatelier principle, the dissociation of ammonium hydroxide decreases. It will produce less OH minus ion concentration in the solution. With these hydroxide ions, these three cations can give their respective precipitates. Ksp value of these three hydroxide precipitates are really less. That is why we can see these precipitates in the presence of this low OH minus ion concentration. If the hydroxide ion concentration is greater, other cations can also form their respective hydroxide precipitates. That is why we use ammonium chloride in the group analysis. The answer is ammonium chloride decreases the hydroxide ion concentration given by ammonium hydroxide. If you want, you can further explain. This ammonium ion acts as a common ion. Therefore, according to the Le Chatelier principle, this reaction goes towards left. That decreases the OH minus ion concentration given by ammonium hydroxide. The second point, it prevents the precipitation of other cations as hydroxide with Fe3 plus, aluminium 3 plus and chromium 3 plus ions. Again, if you want further explanation, you can write Ksp value of these three precipitates are really less. Therefore, in the presence of this less OH minus ion concentration, only these three precipitates can be observed. If ammonium chloride is not present, OH minus concentration produced from this dissociation is greater. Therefore, other cations can also give their respective hydroxide precipitates. This is the answer for the question number 6.